Good morning, everyone. Welcome to WESTalks and to the next session or the spring session of WESTalks 2021. Oops. So just to give a brief intro of WESTalks. So WESTalks is jointly hosted by IC Impacts and UBC Future Waters. So IC Impacts, just for the audience and the speaker, IC Impacts is a pan-Canadian Canada-India Center of Excellence, which serves as a network collaborator for research between India and Canada, particularly working in the area of infrastructure, health, and water. Similarly, UBC Future Waters is a research group hosted at UBC. It's a research excellence cluster. It focuses on interdisciplinary research at the intersection of law, policy, and governance, and applied and biophysical sciences. So just to introduce you to all the members, Abhishek is a grad student or a PhD candidate and a Vanier scholar at UBC. Lady is a postdoctoral candidate at postdoctoral fellow at UBC. Myself, I'm a PhD candidate too. And Carl, we are both PhD candidates in the same laboratory. Jaskaran recently joined University of Guelph as a postdoc, and we have Feria from IC Impacts, who's the event coordinator for and helps us with the process. So welcome to the second week of WESTalks. And as you can see, we have a big lineup of speakers up to actually May. For this week, we have Dr. Minkyu Park from University of Arizona, and I'll be giving his brief introduction pretty soon. Just to let all the audience and the speakers know that all our talks are available on the YouTube website. So if you have missed any talks or if you want to go back and listen to them, you can go to the IC Impacts YouTube page and access all these talks. So introducing Dr. Park. Dr. Park is an assistant research professor in the chemical and environmental engineering at the University of Arizona. He received his PhD in 2016 as at the same school as his MS in 2011 at the Guangzhou Institute of Science and Technology. His primary research focus is on water treatment processes, so particularly areas of water reuse, activated carbon adsorption, membrane separation, ozone oxidation, and UV-based advanced oxidation processes. He's interested in identifying the fate of contaminants of emerging concern, or CECs, throughout water treatment using analytical instruments, including high resolution mass specs. And his talk today is also focused on contaminants of emerging concern. He's a recipient of various grants from the National Science Foundation, Bureau of Reclamation, and USDA, as well as US Geological Survey as a principal and a co-investigator. With this, I'll pass it on to Dr. Park, and we look forward to your talk, Dr. Park.
Thank you for your introduction, Flora. Let me try to share my screen first. So can you see my screen?
Oh yeah, it's
all right.
You can see it.
All right, so today I'm very glad to have an opportunity to present my research area, which is treatment technologies and monitoring strategies for contaminants of emerging concern, CECs, in potable water use. So before actually starting my talk, I want to let you know that you may be anticipated to see a lot of the PFAS work here, but I'm going over the monitoring strategy for the CECs and also some of the treatment technology for the different classes of organic matter too. So please be aware of that before listening to my presentation. So let me start with my presentation by talking about the Industrial Revolution. So since the COVID-19 pandemic started, technology revolution has been accelerated. And now we have a video webinar here sharing my presentation with the people who are far away. This is amazing because geographical location is no longer a hindrance of the sharing knowledge. Another revolution is developing autonomous driving. Many big tech and the growing companies are actively developing self-driving cars. Once this technology has been fully established technologically and institutionally, we don't need to waste our times on the street for driving, and we can utilize our time in a more useful way. Like proceeding the Industrial Revolution, our urban water system has been evolving in a similar manner. So Professor David Sadlock at UC Berkeley wrote a book, The Water 4.0. This book introduces the revolution of the urban water system. Conventionally, our water use and the quality were managed by a centralized system. However, climate change over time is evident, and hydrological water cycle has been also changing. Also, different regions of the world have different available water resources, different population density, and different climates. All in all, such a diversified environment require localized water treatment systems and makes people interested in emerging water resources. Technologies leading urban water 4.0, this includes water reuse, stormwater harvesting, water conservation, and seawater desalination. Among the listed technologies, water reuse will be the most efficient drop-proof method because its source waters, typically domestic wastewater effluent, these are available everywhere. So what is potable water reuse? Potable water reuse is an emerging water treatment scheme generating drinking water from wastewater. So how do we do that? When we produce drinking water, we can do it directly, going from the wastewater through the advanced engineering processes into drinking water. So indirectly, the water reuse is we put the wastewater effluent into an environmental buffer, actually treated wastewater effluent into an environment buffer, such as the groundwater aquifer and the water reservoir. So microbes growing on the surface of the soils and plants can attenuate organic constituents, which is a natural water treatment process. So theoretically, the advance in engineering treatment systems can deal with direct water reuse, but public perception is a major obstacle for its implementation. So water use is more energy efficient than other advanced water treatment technologies, such as seawater desalination. So this graph shows the comparison of the energy consumption per unit volume of the water production. Here, OCWDGW replenishment project, which is the Orange County Water District groundwater replenishment project in California. This is an indirect potable water reuse project. And this project has similar energy efficiency compared to the brackish water desalination. And also it have the 4 times lower energy consumption than seawater desalination, so which is the energy efficient. So while the water reuse has many advantages, it is also true that the contaminants in its water sources, which is generally domestic wastewater effluent, this needs to be better understood compared to those in the conventional water resources, such as surface water. Wastewater treatment plant is a receiving water body of the wastewaters from anthropogenic contaminants. So it receives everything we produce and use. For example, pharmaceuticals, pesticides, personal care products, natural chemicals, industrial compounds, and some of transformation products generated during the treatment processes. So in the regulatory standpoint, it is an almost unachievable goal to try to find out the safety of every possible chemicals in waters. The screen shows a CHEM abstract database showing the number of the compounds registered in the database. The number of the compounds exponentially increased over the 5 decades. Now the number of the registered chemicals is greater than 150 millions, which is quite surprising. But the more surprising thing is we add more chemicals every day. So if we consider such an overwhelming number of chemicals in our lives, it is also reasonable to assume there are many chemicals in our wastewater effluent, which is a receiving water body. So a research paper estimated roughly the more than 80,000 organic chemicals present in our wastewater effluent, so which is a huge number. So since we have numerous chemicals present in water resources for potable water use, some of you may have questions. For instance, what contaminants do we monitor among the various number of the chemicals in our wastewater effluents? And actually, we already know that it is challenging to monitor all possible individual chemicals. So we need to develop a strategy to prioritize the chemicals in our water for monitoring purpose. Also, because of its difference from the water resources for conventional water treatment processes, the water reuse need more comprehensive monitoring strategy to ensure and secure the quality of water. So once we establish a list of compounds for monitoring, the next question would be what treatment technologies we can use to attenuate such chemicals. So I'm going to answer those two questions in the following slides. So in order to achieve infallible monitoring in potable water use processes, a tier structure of the monitoring has been proposed, which consists of the 3 tiers here. The tier 1 is monitoring of the bulk water qualities such as pH, temperature, conductivity, turbidity, and also some other organic primaries such as total organic carbon, UV absorbance at 254 nanometer. So these parameters can often be monitored by real-time online sensors and can be good surrogates for ensuring water quality in treatment systems. The second tier is measuring target compounds. We can use like a liquid chromatography mass spectrometer to measure trace contaminants of the emerging concerns, such as pharmaceutical activity compounds and steroid hormones. So tier 2 is a very specific and useful to monitor contaminants in which we know to have a high biological activity or potency. But we may not be able to capture other important contaminants because it is a targeted analysis. Therefore, more comprehensive advanced chemical and biological monitoring tools will be necessary to complement the target analysis. The last tier, which is tier 3, is the in vitro bioassay screening and non-targeted analysis using high resolution mass spectrometry. So there are numerous chemicals present in the world, and targeted chemical analysis cannot capture all of them. Definitely in vitro bioassay, also non-target screening cannot capture all of them, but it has a broader spectrum to capture. So bioassay measures the overall biological response for the mixture of the chemicals, and non-targeted analysis, typically using a high-resolution mass spectrometer, allows to scan the ionized organic molecules in waters. So these two bio and chemical analytical tools are extremely useful to find unknown chemicals implicated for causing adverse impacts on human health and the ecosystems. Interestingly, the recycled water policy of the California State Water Board, it requires bioassay testing for recycled water project, particularly 2 endpoints, the estrogen receptor alpha and iron hydrocarbon receptor. So there's in terms of regulatory perspective, like the government started showing interest in the importance of the bioassay and also probably non-target analysis too. So the overall tier structure shown here is extremely helpful to ensure the water quality in potable water use. Interestingly, the inverse direction of the tier can be utilized to establish a list of compounds that can be important to monitor. But I mean, that's basically, especially for the chemicals that are not the conventionally monitored. So for instance, we screen what biological endpoints are important in our water, and then what kind of a chemical can cause such biological the responses. So let me show you an example of how we establish a list of target compounds of the monitoring from bioassay screening and non-targeted analysis of the endocrine disruptor. So GR here is a glucocorticoid. So if you are not familiar with this, think about the cortisone and all of the anti-inflammatories. So AR is an androgen receptor, and ER is estrogen receptor. So interesting part of the story is FDA approved the use of Flonase and Nasacort as over-the-counter drugs. So if you go to Costco, you can see pallets of this stuff. So now we can take a look at the bottom left graph, which is the biological response from the in vitro bioassay screening for 3 different endpoints. So it is interesting that AR androgen receptor and the estrogenic receptors, their activities disappear after chlorination. So we can see the black cells here, so which means they disappear. So GR activity persists after chlorination, so indicating chlorination is not really effective for reducing GR activity. So in the meantime, advanced treatment processes such as ozone UV testing here were efficacious for reducing the GR activities. So from the in vitro bioassay screen here, probably GR will be the most important class of the hormones in the wastewater effluent of our interest, since many wastewater effluent treatment processes include chlorination, which is not effective for the GR attenuation. And also the majority of the wastewater treatment do not implement advanced treatment processes such as ozone and UV. So now we know that like the GR activity is important in our water. The next question is, what GR compounds or analogs induced the GR response previously? To address this question, we can scan ionizable organic molecules using a high resolution mass spectrometry. So we use Agilent, the LC, for time of flight mass spectrometer to scan the ionizable organic molecules here. So before that, we decided to fractionate wastewater effluent first using chromatographic separation technique and collected the fractions. So this procedure substantially reduces the complexity of the matrix and enables us to screen potential glycocorticoid compounds more efficiently. Then we injected these fractions to the high-speed, high-resolution mass spectrometry. So at this point, we still see thousands of the compounds in the fraction, and it is still necessary to screen further. So with a statistical tool, such as a heat map with the Euclidean distance, and then narrow down the compounds that are uniquely present in the fraction, in the collective fraction. We found many glucocorticoid compounds in the database, and this is very good because first time we didn't know what kind of glucocorticoid compounds were in our water, but database helped us to figure out and the list of the chemicals potentially in our water. So this is a very helpful for prioritizing the glucocorticoid compounds for regular monitoring. So the next step is we developed the LC triplicate like a quantification method, which is target analysis, and then measure down into the parts per quadrillion, which is very low concentration. So it is like a noteworthy that this LCMS quantification method looks similar with the high resolution mass spectral scanning, but this LCMS target quantification method is generally more sensitive than the high resolution mass spectral scanning. So this is because LCMS method focuses on the selected chemicals, whereas the mass scanning, like the monitor thousands of the ions simultaneously, which ultimately reduces sensitivity. So the first step, we did a bioassay screening. We list up the potential glucocorticoid chemicals using high resolution mass spectrometry. And then we developed a target method to monitor such compounds in our water. So the last part is to evaluate whether the biological activity induced by the selective glucocorticoid receptor compounds match the overall response measured by the in vitro bioassay. So we have analytical data shown earlier, and also we have a human cell data shown earlier. So my question is, does it match? So if it matches, we figure out that what glucocorticoids accounts for biological activity of the effluent organic mixture. So we tested various physical and chemical treatment processes here, like our reverse osmosis membrane, ozone, chlorination, UV photolysis, and a combination of the advanced treatment processes. And then we compare the chemical equivalence concentration with a bio here like a bioassay equivalent concentration. So here the chemical equivalent concentration is a dexamethasone equivalent concentration that considers individual compounds potency and the concentration. And the here bioassay equivalent concentration, which is a biological response of the mixture. So basically, it looks a bit complicated, but the simple message from this graph is if you see the black solid bar is similar to the sort of open the bar, which means the chemical equivalent calculated from our target analysis matches overall biological response measured by the in vitro bioassay. So we see the very good agreement, which means the list of the chemicals from the high resolution mass spectrum scanning, actually it accounts for the majority of the glucocorticoids inducing biological response in our wastewater effluents. All right, so let me move on to the next slide. So so far, we established a targeted list of the glucocorticoid compounds from bioassay screening and non-targeted analysis. The next interesting thing is why this class of compounds were removed well by advanced treatment processes like RO membrane. So let me go back. So RO can remove the glucocorticoid activity substantially. So at high ozone dose, ozone was effective too, whereas chlorine is not effective at all. And the UV photolysis was also effective for attenuating GR activity. So, so the question we can have here is the why this class of compounds were removed well. So, and also we will be interested in the what other treatment processes can be used to attenuate GR compounds. So we can find an answer from its chemical structure shown here and the properties. So let's take a look at the structure of the triamcinolone acetonide, which is one of the glucocorticoid compounds first. So one noticeable structure information here is a diene group, which is highlighted in red with the vesicle. And then the diene group consists of the olefin, double carbon-carbon double bonds, and the carbonyl group. So here, like the olefin group is electron-rich, and then ozone is well known to react effectively with electron-rich moiety. So, and it is reasonable to assume ozone is efficacious for attenuating this compound. So chemicals with the dienes, such as santonin, is also known to be photoreactive. So we can also assume that like these chemicals of the effectively removed by the UV photolysis. Also, we can take a look at the molecular weight, which is 434.5 gram per mole. So which is fairly large molecules. If we think about the molecular weight cut off the RO membrane generally for between 100 arton to 200 arton, we can assume that the RO membrane can reject this large molecule. And also another interesting property shown here is the low KOW, which is octane water partition coefficient, which is an indicator of the hydrophobicity of the compounds. So the value 1.9 means it's a fairly hydrophobic, so it can be removed by the activated carbon. So chemical structure can be a hint for the selection of a treatment technology. So we learned the two treatment processes are efficacious, two chemical treatment processes are efficacious for the attenuation of the glucocorticoid compounds, UV and ozone. So previously, we utilized a high resolution mass spectrometry to screen GR active compounds. Here, we can also utilize the same instruments and same technology to study kinetics of the GR compounds degradation and its transformation pathways. So this graph shows that attenuation of the selected the glucocorticoid compounds. We developed almost 30 glucocorticoid compounds during the target analysis, but we selected some of them for the studying its degradation in UV photolysis. So the compounds if you see the left graph, you see some of the compounds degraded rapidly, whereas some of the other compounds degraded slowly. So the compounds, so we can simply divide this compounds group into two based on the functional groups and the kinetics. So compounds with a slow degradation has one double bond, double bond in the 6-membered ring, which is the anon group. Compound with two double bonds, which is dianon group. So when we look at the kinetics, dianon group, the compounds have a faster, the higher reactivity with in the UV photolysis process compared to the anon group with a single double bond. So chemical structure is very important for determining the reactivity of the glucocorticoid compounds in photolysis process. And interestingly, we tried to look at the degradation pathway in photolysis, and then we saw that isomerization is the primary transformation mechanism of the glucocorticoid compounds. So this is particularly interesting because even though photolysis does not add or subtract the elements, which means the produced chemical is an isomer of the precursor, the just different structure do not induce bias response shown earlier. So chemical structure is also important for the bioassay activity. So in the earlier slide, the UV was effective for the compounds with the two olefins, the dianon group. However, ozone shows an opposite trend here. So 3 GR compounds here, like a FCA, CBP, and TCA on the right graph, here have very lower reactivities with ozone compared to the structurally similar compounds with a single double bond, including the 3 compounds at the top, right? So this difference can be explained by the delocalization of the molecular orbitals. So we calculate the delocalized orbital energy using a quantum chemistry simulation. So that is the energy, the EMBO here on the right graph. This energy, the localized energy, was linearly correlated to the reactivity, suggesting the importance of the electron delocalization in ozonation. So the UV is effective for the compounds with the 2 double bonds, whereas the ozone is more effective for the compounds with a single double bonds. So, and also we try to look at the transformation mechanism of these transorganic compounds. And so the molecular orbital is actually the localized on the double carbon double bond here, and then so the ozone is attached and reactive with this the electron rich the function group. So first it formed the ozonide, and then it followed by the formation of the tellurionic ion. So here eventually, so eventually we form the chemical with one less carbon. So this transformation pathway is often called anomalous ozonation because it's not widely observed a long time ago. But now, since ozone has been actively studied, as far as I'm concerned, it cannot be called anomalous any longer. But the point is the high resolution mass spectry can capture this transformation pathway, and also the structural information of the glucocorticoid compound is very important to think about the transformation pathways. So far, we saw the selectivity of the enon and dianon groups in photolysis and ozonation. So selectivity is extremely useful to guess the reactivity of molecules in chemical reactions. However, physical separation can utilize both selectivity and non-selectivity. So let's take a look at the per and polyfluoroalkyl substances called PFAS. So PFAS has the chain of the aliphatic, the alkyl chain substituted with the fluorines. This part of the functional group is not favorable for chemical reaction because of its high bonding energy. However, this structure group to make PFAS more hydrophobic. So hydrophobic interactions are non-specific. It is related more to its compatibility with solvents and solid surfaces, which is generally absorbent. For instance, activated carbon adsorption for hydrophobic compounds removal is effective since hydrophobic compounds are not compatible to water and prefer being partitioned onto solid surfaces. So PFAS also has acidic groups that are negatively charged at an environmentally relevant pH value. So we can think of this property when come up with the treatment technology. So this, the left graph shows the adsorption result in a fixed bed absorber. So y-axis indicates the normalized effluent concentration, whereas x-axis indicates the throughput in the unit of bed volume. Interesting part is that adsorption capacity, that is represented by the bed volume 50 here on the right side graph, is linearly correlated to the hydrophobicity of the PFAS for both carboxylic one and the sulfonic one. So this gives us an important message that non-specific hydrophobic interactions plays a predominant roles in the adsorption in activated carbon. So previously, chemical reaction utilizes the specific chemical groups to react with, but the physical separation, actually the maybe compatibility, especially in adsorption, may be more important for removing the PFAS here. So anion exchange resin is another the physical treatment process effective for the PFAS removal. So our organizer Flora is an expert in this area. So yeah, so also I assume that our next speaker, Dr. Atiyah, he would cover this topic in detail, I assume. So let me show you my results briefly here. So the left graph shows that how much PFAS was absorbed on the unit volume of the resins. We use the magnetic ion exchange resin called MIX here. So as we expose PFAS to the resin, PFAS were rapidly absorbed onto the resin surfaces. So interestingly, the total negative atomic charges, which is x-axis of the right graph, the total negative atomic charge was correlated to the equilibrium constant of the adsorption, which is a y-axis. So this suggests that overall charge interaction are important in the PFAS removal in an anion exchange resin process. So when we look at the charge distributions here, those are calculated by the quantum chemistry simulation. The core carbons were positively charged, while the fluorine and the oxygen atoms of the acidic groups are negatively charged. Since the PFAS molecules were distributed by these negative charges, it is also reasonable to postulate that the charge interaction with a positive charged solid surface would be more important than non-specific hydrophobic interaction that were important in activated carbon adsorption. So in this presentation, we went over monitoring strategies for contaminants of emerging concern. And I was trying to think about the selection of treatment processes based on the chemical structures and properties. So potable water use is extremely emerging. I'm not extreme, actually relatively emerging. And it has many issues to resolve, such as a negative public perception. However, I expect bright futures to secure the safe drinking water across the world, but more cost effectively, particularly with the potable water use technologies. So we are scientists and engineers, and I hope we can further advance treatment technologies and the monitoring tools in potable water use so that we can contribute to resolving water issues in the world. So I would like the express my appreciation to especially Dr. Shane Snyder, who is my former advisor, and he's currently in Singapore now. And also, I would like to appreciate Doctors Jia, Yu, Anmo, Wu, Opejans, Daniels, and Lopez, and also other former colleagues, Sean, Austin, Joe, and Derek, for helping the presentive work. And also, I would like to thank the Agilent technology for providing the analytical instrument, the technical service for the analytical instrumentation. And so I would like to appreciate the Xylem for providing the ozone system, carbon-carbon cooperation for providing activated carbon, and XM for the providing anion exchange reagent. So thank you so much for your attention. Now I'm more than happy to answer your questions.